Let's start with L2 design principles. The most important thing about L2s, of course, is that they are built on top of L1s. And what that means is that if you're designing an L2, you don't need to build yet another large economically secured consensus. Large economically secured consensus is the most expensive part of an L1 system. Ethereum has about $90 billion of assets staked in the protocol and pays out several $billion a year in rewards to block proposers. That's super expensive. If you're an L2, you don't have to do that because you're building on top of an L1, right? You rely fundamentally on the L1 consensus. You rely on the ability to have an L1 smart contract act as a trusted referee, or in computer science or distributed protocol terms, a trusted third party within your protocol. And the ability to have a trusted third party that executes as a smart contract is incredibly powerful in enabling the design. Also, this allows you to take different designs and to use a design that's much lower cost. The second is that the result of that is a significantly different design space. As just one example of this, L1 consensus, like in Ethereum, you have this issue of chain reorganizations, where a block is published, but then it turns out eventually not to be canonical. And of course, that happens every day on Ethereum. To give an example of what you can do in L2 design, an Arbitrum 1, in about 3 years, there's been one reorg affecting 3 transactions. So statistically, the odds of your transaction being affected based on history by a reorg is about 3 times 10 to the minus 8. And this has this has powerful effects for users and user experience, because if you know that the chain will almost certainly not reorg, it means that you can act on a block when it has been produced quite quickly with not a guarantee, but a very high confidence that it won't be reorged. And that's a thing you can do in L2 design that's very difficult to do in L1 design, because with L1 you have to deal with all of those issues of consensus in a partially synchronous network and so on, as suggested in Tim's talk earlier. Number 3 is that it's actually useful in designing an L2 to decompose the protocol into different functions, different sub-protocols, if you will, that are designed to work together, but that have different, but also are designed sort of as distinct components, because they have different needs and crucially operate on different timescales. I'm going to show a diagram in a minute of one way of decomposing the design of an L2 into 4 components. But I'll note now that some of those components operate at a timescale of around 250 milliseconds, and others operate over a timescale of days to weeks. And of course, what follows from this, importantly, is that if you want to think clearly about L2 design, it's important to not get too locked into the mental models and assumptions that you might have learned in thinking about L1 design, because it's a very different problem. And then finally, if you're designing an L2, there's more space to innovate, but L2 systems are not test nets, right? Many people have put a lot of valuable assets, invested a lot of effort and energy in using L2 systems. And so there is a responsibility to be careful in the design and operation of these systems. Okay, so here's basic roll-up design. This is how, at least, I sort of think at the highest level about the design of Arbitrum, or really almost any L2 roll-up type system, as having an L1 network at the bottom, Ethereum in the case of Arbitrum 1, and then the L2 protocol itself having 4 components: sequencing, execution, data management, and proving. And let's go through what those do. First, you have the sequencer. The sequencer's job, and its only job, is to receive incoming transactions that users have submitted and to put them in order and to publish an ordered list of transactions that have arrived at the chain. That's all the sequencer does, all it's trusted to do. And as I said, I'll deep dive into sequencer design in a minute. But it's really important. There are many misconceptions about the roles of sequencers. And so I'm going to say this again. Its only job is to put transactions in order. It's not trusted for anything else. Once you have an ordered list of transactions, there are 2 things that you can do with it. First is execute. So the execution basically takes this ordered list of transactions and produces a sequence of blocks according to a deterministic state transition function. And because the sequencer is publishing its sequence, and everyone can see that, and because this state transition function that builds the blocks is deterministic, it means everyone can compute for themselves locally what the blocks of the chain are if they have reliable access to this ordered list of transactions. And this is actually important. You don't need to reach consensus on what is the result of computing these things. You can compute that for yourself if you have reliable information about this ordered list of transactions produced by the sequencer. And most nodes on an L2 chain operate just that way. They compute, execute the chain for themselves. The next piece is data management. What data management does is it takes these transactions in order as published by the sequencer almost immediately in a continuous feed and records them on the L1 chain. That means that they are either bundled up into call data, or on Ethereum, they're put into EIP 4844 data blobs. But the data management, for efficiency, will typically build up a batch of these transactions, get a nice big batch, compress them. And by compressing, you can gain about a factor of 3.5 in the size of that data. And that saves you a factor of 3.5 in data posting costs. But this component receives these transactions in order, batches and compresses them, and ultimately pushes them onto L1. Now, because, again, this is a deterministic execution function, once these transactions are recorded on the L1 and have finality there, now these transactions have finality in the sense that anyone can compute the result of the transactions for themselves. And you know that although proving hasn't happened yet, you know that there is one and only one result that can be proven. And so this is the moment of finality when the transaction is recorded onto the L1 by data management and has finality on L1. So that's about that. What that means is that a well-designed L2 gives your transactions finality basically at the same speed as L1 finality. And then finally, you have proving. And the job of proving is simply to prove to the L1 what the result of execution is. That is, you prove to the L1 that if you execute the transactions as recorded by the data management component onto L1, that the result will be some sequence of blocks, right? And Ben's talk just now gave a pretty good explanation of how proving works in an optimistic rollup. But optimistic or ZK, bottom line is you prove this to the L1. Now, most nodes already know the result before you do the proving. But the purpose of proving is, first of all, to tell the L1 what the result is. The L1 can't compute all of this stuff. It doesn't have the horsepower. It doesn't have the throughput to do that. But also, it's really useful to have a certified and settled version of the result of the L2 that is recorded on the L1, because it lets people who want to catch up to the current state get a good, known good canonical checkpoint of the L2 state. Yes.
So this might be premature, so feel free to.
Okay.
Given the context given, what does it mean to have a reorg on the L2?
Yeah, what it means to have a reorg on the L2 essentially is that there's two ways this can happen. One is if the sequencer equivocates. That is, the sequencer tells you one version of the transaction list that came in, but then somehow another version eventually gets posted onto the L1 and becomes canonical. That would look like a reorg. The other thing that I didn't show here is that these systems have a fallback means of getting your transaction included in case the sequencer is censoring you. And that is, they typically have a mechanism by which you can post on the L1 basically a transaction that you would like to be included, and then the data management mechanism, if the sequencer is, I'll get to this in a bit, the sequencer is encouraged to interleave that transaction into its sequence. But if it doesn't, the data management component will cram it in anyway. And that means that your transaction, the sequencer doesn't have the power to censor your transaction. It can only delay it. The other way a reorg can happen is if the sequencer ignores one of these transactions that sort of came in through this fallback mechanism, then the data management system will cram it in, and that may also cause a reorg.
So to clarify, the sequencer is not like an unconditional authority on the sequence of transactions. There are cases in which
There are cases in which the data management will overrule it, but only when the sequencer is misbehaving. If there's a well-behaved sequencer, then the sequencer's
That's all observable because it's happening on the L1.
right. That's right. The fallback happens on L1, and so and that's why the sequencer can't stop you from doing it.
Where the data management for the posting is sequencing, is that the dispute resolution?
No, the dispute resolution protocol is all over here in proving. So the sequencer is actually, let me defer a little bit about the semantics of sequencing because I'm going to deep dive into sequencing in just a moment. But yes, a question here.
Callback.
Mhm.
So if you deal one together with your block, it's like a sequencer. But then you're executing based on the sequencer, like how does that?
Right. So here's the way this works. If you want, you have the option of sending a transaction to what I'll call the L1 inbox, right? And then the sequencer is instructed to, but might not if it's badly behaved. It's instructed to interleave that message into its sequence. That's the normal case, right? And if it does so, great. Nothing else has to happen, right? But if the sequencer doesn't do that, then after a time interval, you can go back to that L1 inbox and say, you can go back to one of the L1 smart contracts of the protocol and say, hey, I put my transaction into the L1 inbox and the sequencer didn't interleave it. And then the data management system will cram it in whether the sequencer likes it or not. So the data management system in that case overrides the sequencers. It sort of injects that into the history. Yeah, there's a little sort of dotted line that you can go down to the L1 and then that comes back up into data management. That's something that exists only as a fallback in case the sequencer is misbehaving. And so that's only happened once. That's happened only once on Arbitrum 1. That was the cause of the reorg that happened, is that the sequencer, due to a software bug, was unable to include a certain one of these transactions. And so it ended up getting forced in.
And so just to
Yes.
clarify, so the
Yep.
proving part is only coming into effect when there's a challenge, or is there generally a proof provided?
So the proving part in an optimistic rollup, the way this typically works is normally one party asserts the correct outcome and stakes on it, and nobody disputes that. And after the challenge period has passed, that's accepted by the protocol. That's the normal case. But if there are multiple parties who disagree on different block histories here, then the dispute protocol that Ben talked about will come into play. But that's an exception because if parties are rational, that will never happen.
And the assertion is coming from?
The assertion can come from, in bold, it can come from literally anyone. Anyone who's willing to stake on an assertion can do it. And the guarantee in the proving protocol is that if there is at least one honest participant in the protocol, and if the L1 chain is safe and live, then the proving protocol will get the correct result. But I do want to set aside proving because that's in some ways interesting, important, but also orthogonal to what where I want to go today. Yes, one more.
So
Quick, yeah.
The L2 state has transitioned. Is that like after somebody asserts in the proving stage and nobody?
L2, I'm sorry?
So
L2
the state of the L2. I'm trying to understand what is the point at which the state of the L2 has transitioned. So for instance, once the sequencer has put transactions in order, I'm guessing that's not any sort of finality
So
of the state transition.
here's the way to think about here's a good way to think about finality. The sequencer in a fraction of a second publishes, you submit a transaction to the sequencer. Typically in a fraction of a second, it puts that into the real-time feed of transactions that it's publishing, right? And that is, that's what you might call a pre-confirmation or a soft confirmation. What that means is if the sequencer is honest and doesn't crash, that your transaction will eventually become final. But it does come with that caveat. Then eventually your transaction is put into a data batch that by the data management scheme and then posted onto L1. and gets finality on L1. Then your transaction has finality, because then the result of it is fully determinable by anyone, right? Anyone can get your transaction because it's on L1. Anyone can execute for themselves, get the single unique deterministic result of your transaction, right? Finality means that there's only a single result possible and everyone can know what it is.
Posting.
Then, sorry?
Posting could be wrong and that could be challenged.
But no, it can't be wrong, because all it says is this sequence of bytes arrived at the sequencer, right?
That be misreported is what I'm saying. Like
Yeah. Let me put aside the question of misbehaving sequencer until I dive into the sequencer. But the key thing is that
I was thinking whoever is posting to the L1
Yeah.
sequencer, or is it somebody else?
it could be the sequencer, it could be somebody else, depending.
Somebody else is the misbehaving party.
So the sequencer does sign its feed, right? And you need to make sure that what gets posted here is consistent with some feed that the sequencer signed.
Right.
The sequencer could still equivocate, right? And that's a reorg. But the sequencer here is just reporting that certain strings of bytes arrived as transactions, right? It's not claiming anything about whether those transactions are valid, even, or what the result of executing them might be. Yeah.
One more time.
Mhm.
Suppose the sequencer is fully honest, doing everything
Yep.
it's supposed to,
Uh-huh.
and then somebody else posts to the L1 saying this is the batch, but let's say omits one transaction or does it maybe even puts in something that sequencer didn't actually put out there.
Yep.
And posts that to the L1.
Right.
In that case,
Now, the protocol needs to make sure that what gets posted is something that was endorsed by the sequencer.
everybody can post. Like, so I guess the sense of
Well, no, if the sequencer is signing its feed,
yeah, so I'm saying
right, anyone can post that signed feed.
everything that is posted will count as having been posted.
Not necessarily, right? That's right. If you just make up a bunch of junk and try to post it, the protocol will reject that. It will essentially say that's not a valid data batch and will ignore it. It will be a no-op. So you have spent a bunch of money posting a big piece of data on L1. You'll have bought a bunch of L1 gas. You will not have affected the outcome of the protocol. All right, cool. Let's move on and talk about the sequencing piece. And again, start with basics. First, the role of the sequencer. The role of the sequencer is to produce a canonical sequence of incoming L2 transactions. It's just saying, these are the transactions that have arrived, and this is the order in which those transactions should be executed. It also has the job of interleaving into that sequence transactions that were submitted on the L1 chain. I talked about that a little bit ago. People can post on the L1 chain some transactions. You might do that if you worry that the sequencer is censoring you, but typically that happens because you, quote unquote, you in the story are an L1 contract. And if you're an L1 contract, you can't digitally sign a transaction and then like send it across the internet to the sequencer. All you can do is make a call to the L1 inbox contract and say, here is a transaction I want to have sent to the L2. So the sequencer reports on what it received, in what order, and it interleaves the transactions submitted on the L1 chain. Things that are not the sequencer's job, it's not trusted by the protocol to vouch for the outcome of transactions. It can include invalid transactions. The protocol does not trust the sequencer to only include transactions that are valid. But for reasons I'll explain later, a rational sequencer will not include invalid transactions, basically because it will get slashed a little bit if it does. Also, the sequencer is not involved in setting fees or collecting fees. There's this term sequencer fees that people use. I don't know why people use that term, because I think at least on Arbitrum and I think on other well-designed chains, the sequencer does not decide what the fees are. It doesn't collect the fees. It never has the money. And so fees are really independent. And importantly, the sequencer, whoever that is, or the method of choosing it, sometimes there are multiple sequencers. It might be a committee, whatever it is, typically are designated by chain governance as part of the chain's business to decide who plays that sequencing role.
What's the objective function of the sequencer? Does he want to maximize anything? Like how does he pick the order?
Well, the sequencer is hired by the chain, right? and so generally paid by the chain. The sequencer never has their hands on MEV money, at least on Arbitrum. And so it doesn't have a direct profit motive to maximize MEV. Those may be its instructions, and the protocol will deal with MEV. But generally, the sequencer's job is to play this role on behalf of the protocol. I'll talk a little bit about incentive issues as we go on.
Did they have a specific reason to pick an order over another, or?
Yeah, I'll get to that. That's one of the key questions is how does the sequencer pick the order? Yeah, all right. So there are different approaches to sequencing, which really go to this question of what is the ordering that comes out. And sort of the first line I would draw or division in the taxonomy is the builder auction approach versus policy-based sequencing. The builder auction basically is kind of like what happens on Ethereum, that for each block, you divide time into blocks and you somehow auction or sell or give out the right to build each block. If you do this, you basically have a setup that will operate very similarly to Ethereum. You'll have the same you expect the same dynamics to emerge, the same economics. That's been much discussed. The main difference would be that the block time is typically much shorter on an L2. So the equilibrium, right, is you get a lot of extraction by the builder pays the chain, and the chain gets that revenue. The other approach, which is more commonly taken by L2s, is what I'll call a policy-based approach. And there is some specified policy that's specified by the chain or by the protocol, and the sequencer is supposed to follow it. Now, the sequencer is chosen by governance, often paid by the chain, and so the sequencer may have an interest from reputation or an interest in continuing the the flow of fee-for-service payments from the chain to do its job in order to do that. But the basic, and sometimes the policy will be partially or totally checkable. And of course, if it is checkable, then it will be checked by the protocol. You can also use a committee sequencer. That would also be chosen by governance. And then you have sort of the obvious the threshold honesty assumptions about the committee. Okay. But the key idea here is that there's a policy the sequencer is supposed to follow, and you rely on either trust or you rely on incentives that are managed by governance to get the sequencer to actually follow that policy. And of course, the next question is, well, what might that policy be? But the other thing is I'm going to focus on this, on the policy-based version, and for a couple of reasons. First, builder auction is much like Ethereum. That's been well studied. There's been several talks today, quite a few actually, about what happens in the economics of a system like this. I want to focus into these kind of systems. What are the policies and what emerges? Also, this is what the major L2s tend to actually do. Okay. One of the things that's common across L2s is the use of a secret mempool. When you're in policy-based sequencing, typically you have a secret mempool, and the property you get is that it's not possible for an arbitrary party to see some transaction in the mempool and then submit another transaction that will be sequenced before that, the transaction they saw. So this is like a classic sort of front-running story, right? That I see some transaction, I put my transaction in front of it. Also, this is one piece of sandwiching. And so the property here, because the mempool is secret, and nobody gets to see a transaction until its position in the sequence is already sufficiently locked in that nothing new can be put in front of it. This might be done by the use of, well, I'll talk about how that works later. This prevents some extractive forms of MEV. It prevents simple front running. It prevents sandwiching. It allows, of course, forms of MEV that react to information as it becomes available, such as arbitrage or backrunning. Right? How do you implement this? There's basically really two ways. One is say, well, we're going to send our transactions directly to the sequencer, and then we're going to trust the sequencer to keep that mempool secret. Now, if the sequencer is actually selling front running out the back door or doing front running itself, there are some tricks you can use to prove that it's doing that. That's sort of beyond the scope of this talk. The other way you might do it is some kind of encrypted mempool type approach, where the transactions are encrypted, and they'll only get in such a way that even the sequencer doesn't know what's in them, and that they'll only get decrypted once their position in the sequence is locked in. And again, there's not time to talk about different encrypted mempool approaches, but these are basically the approaches. Most L2 sequencers today use the first approach. They trust the sequencer not to exploit their knowledge and to keep the contents of the mempool, that is transactions that have been submitted, not yet locked into the sequence, to keep those secret from any parties who might want to use that information.
What's the downside to the encrypted mempool case?
Encrypted mempool, typically it's going to be slower, and all of the encrypted mempool approaches have different drawbacks. So for example, you might say, we're going to have the transaction submitter encrypt their transaction, then we'll sequence it, then they decrypt it. But what if they don't? Right? You need to deal with that case in the protocol. You can try to slash them, but then you're still giving them an option on whether they decrypt or not. What if they're just slow? What if they crash? That becomes an issue. You can use some kind of threshold encryption type approach where there's some committee that will decrypt the transactions after sequencing, right? And then as long as a sufficient quorum of that committee is honest, you know that the decryption will happen and that the information won't leak. That tends to add more latency than you'd like to the process. You have key management issues. Encrypted mempool is not compatible with legacy wallets. So users need to then submit through some intermediary that will do the encryption for them. So there's no deep reason not to, but there are a bunch of good shallow reasons not to, at least today. All right, so secret mempool is something that I'm further going to assume from now on. Yes.
Is there any way for the protocol to ensure that the sequencer is not doing something like requiring out of band that transactions be sent in an encrypted form before it includes the encrypted form?
Yeah, so this is one of the issues with an encrypted mempool. If the sequencer is willing to extort people to get them either to just send them transactions in plain text, I'll encrypt it for you, or else it could also extort them to basically submit encrypted, but open their encryption. So that's right. Yeah. Yeah. So encrypted mempool doesn't prevent, and in fact, you can't prevent, for cryptographic reasons, you can't prevent the sequencer from demanding that people basically show their cards when they submit encrypted transactions. Right. Okay. So let's talk about popular sequencing policy. Yes, one more question.
So regarding the identity of the sequencer,
Mhm.
I mean, in practice, how much relational trust does there exist between an L2 and the actual?
Typically quite a bit. Usually the sequencer is operated by some company that has reputation and brand equity in the operation of the technology. So often it's so for Arbitrum 1, for example, it's our company, Offchain Labs. We currently operate the sequencer. We could be fired tomorrow by the Arbitrum DAO or foundation. You know, there are others ready to step in if that happens. But obviously we have a lot of reputation at stake in not being crooked in how we do it.
Do you also have a lot of Arbitrum tokens, like in the governance process?
No. We as a company do not. We as a company do not, and insiders in our company have publicly pledged to and always have refrained from voting in DAO governance. All right, let's talk about popular sequencing policies. I'm going to start with first come, first served. It's the easiest to understand, and I'm going to sort of talk through some of the economics of MEV in first come, first served and how first come, first served sequencer works. And then as a basis for jumping off to two other sequencing policies that are either existing or proposed. One is priority gas auction, which means within each block, you sort in decreasing order of some tip, which is the priority fee in Ethereum. And the second one being time boost, which is first come, first served, except that you auction off exclusive access to a small time advantage. I'll talk about what each of these are And then I'll talk about sort of what are the implications for the economics after talking about first come, first served in a little bit of detail.
So you said before that the sequencer just gets paid for by the protocol?
Yes, fee for service.
And
typically.
then the tip that we have here in the
Goes to
PPA
the chain.
goes to the chain.
Yeah, so the tip, if the tip is the priority, the Ethereum priority fee, right? In execution of Ethereum, the chain itself collects the priority fee. It pays it to the Coinbase address, but in L2s conventionally, the Coinbase address basically is the chain itself. It is in a DAO governed chain like Arbitrum 1, the Coinbase address of every block is the DAO treasury, which means funds go to the DAO, which is the governance of the chain. And the way I think of this is that this is revenue that belongs to the chain, and chain governance should and does decide where it goes. That is, it's not revenue of the sequencer, right? Because first of all, because it's collected on chain as part of the execution of the chain, right? It is, it's not a side payment that's made in any way. Yes.
Chain pay to the sequencer in a sense that, like, depending on his choices, like they might prefer one or another method, right? Depending on
Yes.
whether the gas fee tips are
Well, so
high or not.
right. So the way this works in practice is that there is some governance mechanism for the chain. That governance mechanism instructs the sequencer which policy to follow, and it also pays the sequencer. Typically, that is a fee for service. That is, it's like a certain amount per month or per week. That is, but it's like a service. It's like an infrastructure service that's provided to the chain, and the chain economics are independent of the sequencer. That is, typically the sequencer does not make more money when the chain makes more money.
And just a quick question, just more about the economics.
Yeah.
So because the data management fee
Yeah.
for the
Mhm.
blob has to be paid.
Yes.
And that's paid for by.
That is paid for. The way that typically works is it's paid for by the data management component. And then there's an L1 contract, which puts a message into the inbox, the L2 chain's inbox, saying how much was paid. That message goes up to a trusted contract on the L2, which then which now knows how much was spent for data, and this L2 contract basically puts a tax on L2 transactions. So it is a trusted on-chain mechanism which knows how much was actually spent to post the chain's data, and then imposes a tax on the L2 chains. And that tax is, at least in Arbitrum chains, is dynamically adjusted to make sure that the collections equal the spending on L1. So basically, a way to think about it is that every transaction in L2 gets charged a fee for data posting, and that fee is set in such a way programmatically that the books balance. That is, the total fees collected on L2 equal the total spending of the data poster on L1, not including batches that are rejected as invalid. For those, the data poster has to eat the cost. But if it's a valid batch, as verified by the L2 code, then the data poster will get reimbursed. So if you're doing data posting, you're paying on L1 every time you post a batch. But the L2 chain, you're paying ETH on L1, but the L2 chain is collecting ETH from the transactions that run on L2 and depositing them into your L2 chain, into your L2 account as a reimbursement. And that whole monitoring and reimbursement mechanism is all managed by on-chain contracts.
So, and since
Yeah.
because we're having the tips here and then there's payments involved here.
Yeah.
So if I make a transaction on an
Yeah.
L2,
Yep.
I make the payment, the tax, I pay my tax.
Yes, that's
a-
collected by the L2 chain's trusted code by its state transition function.
Okay.
And it's deposited. So you pay, you run your transaction, it uses a certain amount of gas. There's a base fee and a priority fee, the tip, right? That's taken from your account, just like on L1. And a portion of that will get deposited to the data posters account. as that is the portion that is allocated by the by the data economics contract that what it has assessed to you, and the rest will go to the chain governance.
And I pay this in what currency?
ETH. Yes.
Follow up on that. What happens if the fee to post the
Mhm.
state on L1 is larger than collected fees?
Right. So that can happen. So what happens is that that can happen. What will happen is that this this data economics, these data economics contracts will impose a slight surcharge on future L2 transactions in order to make back the deficit.
Is depositing who is covering the difference
So
in the meantime before it's collected?
yeah, the data poster is effectively lending the money to the chain. Yeah, if that happens. Yeah, that's right. All right, let me keep going here. All right. Let me talk about first come, first served. Okay, here's what happens inside a first come, first served sequencer. You have a bunch of front ends. You need front ends because this is a public internet service, and so people throw enormous amounts of garbage at it, and you need pre-filtering so that you don't get completely swamped with spam and denial of service with all kinds of junk. The stuff that passes through pre-filtering goes to an intake component. Its only job is to receive these things and put them into a transaction queue. And then on the backside, you have this block builder, and its job is to eat the transactions from the queue and build blocks, group them into blocks. Okay. Now, what's inside the block builder? Let me talk about the block builder code here. So it sits in a loop, and it basically, here's what it does. First, it sleeps until it's time to make the next block. Then it creates a new block that's initially empty. And then there's a loop where it says, well, as long as there's something in the queue to put into this block and the block's not full, I'm going to take the first thing out of the queue. Then I'm going to check if it's valid, meaning does it have a signature? Is the nonce right? Does the sender of it have the funds to pay for it? If not, I throw it away. If it is valid, I'm going to execute it and update my internal state. Then I'll append the transaction to the block, and I'll keep going until eventually the block is full or the queue is empty. Then I'll publish the block and sleep until next time. So this is the basic mechanism. And importantly, this step is the bottleneck. This is one of the bottlenecks in the throughput of your chain, is the fact that the sequencer needs to execute every transaction. Now, if you were paying careful attention, you heard me say before that the protocol does not trust the sequencer to say what the result of execution is. But in fact, and it doesn't, but that's not why the sequencer has to execute these transactions. The reason is that the sequencer needs to know which transactions are valid, and whether a transaction is valid depends on the current state of the chain when that transaction gets to the head of the queue. And so in order to know in order to reject invalid transactions, the sequencer needs to actually execute them. But why does this? But I said before also that the sequencer isn't trusted to reject invalid transactions. Why does it? And this is where the sequencer's incentives come in. There is this reimbursement back to the, there is a reimbursement for the data costs of posting the transaction. If the sequencer includes a valid transaction, that transaction will ultimately be charged for its data posting costs as part of this mechanism I described before. If the sequencer includes an invalid transaction, then by definition, there's nobody to pay for the data posting costs of that transaction in order to reimburse the data poster. And so the sequencer gets slashed a little bit to pay for that. Sequencer doesn't want to get slashed. And so it wants to do this. In fact, if it didn't do this, then you'd have a horrible free riding problem. The sequencer would be operating a free data availability service for everyone on the internet. Because you wanted to post some data on Ethereum at no cost, you just make it into an invalid transaction, submit it, the sequencer will pay for you posting it, right? Sequencer can't have that. You can't, and so in order to get the incentives to line up, the sequencer has to execute these transactions. And the result is that if the sequencer is rational, only valid transactions will get posted.
Just to clarify,
Yes.
you mentioned slashing a couple of times. So the
Mhm.
sequencer has to stake something, or and like, if so, what are the capital requirements?
This is quite small, right? Because you just need to know that you can collect the data posting costs for invalid transactions up until the time that the sequencer gets fired.
But there is some minimum capital that you have to.
Yeah, it's not very much.
Okay.
Yeah, data posting is relatively cheap, and so this is not very expensive. The larger capital cost involved with data posting actually is the data poster's own cost to post. It's we could go deep on that, but that's part of the economics of the data poster, and the data poster needs to be compensated for that. But anyway, this is something that needs to happen in order for this whole mechanism to be incentive compatible, in the sense that every transaction that gets data posted gets paid for by someone, and the sequencer is not allowing everyone to free ride on its on these data posting slashes. Yes.
Understanding something, but like, what prevents like the same transaction being like executed by various sequencers like before it gets posted?
So in this scheme, there is one sequencer. If you have a distributed sequencer committee, that's really beyond the scope of this talk. But what you want from that distributed sequencer committee is to do something that is that behaves like this in a distributed way, and that's like way beyond the scope of this talk, how that would work. But with the centralized sequencer, it would do this. With the decentralized sequencer, you have to do something a little more complicated.
So
Yeah.
the concept of block time
Yes.
seems to be slightly different again from an L1 in the sense that when it's like 250 millisecond, the time from which
Yeah.
it runs.
Mhm.
But say that at some point I have a lot of transactions, takes longer to form a block, and then
Yes.
then maybe the next time it runs, there is one transaction and immediately I post it.
Block time is variable on Arbitrum chains.
Okay.
It can be longer, although note that the block can be full. There's a max gas that can go into a block, and so there is an upper bound. On a chain that's not very busy, also, you don't make empty blocks. So if you get to this, it's really sleep until it's time to make the next block and the queue is not empty. So the block time can be variable.
So I have a question, like previously we mentioned about secret mempool or something, like the sequencer cannot see what
Yeah.
transaction it is. But you said like here the sequencer need to execute the transaction. So how does
Yes. So how does the sequencer well, the sequencer, it executes every transaction, so it knows the current state because it just executed the last transaction. So the sequencer actually has an execution engine built in, and it does execute all of the transactions.
the sequencer can see the transaction?
Yes, the sequencer can see the transactions. If you have an encrypted mempool, you have to break this apart into two stages, right? First, it makes sort of an encrypted block, and then you have to have another pass where after decryption, it goes through and filters out the invalid ones. All right, let's talk about now MEV a little bit. So in this kind of scheme, essentially all of the interesting MEV happens as some kind of a race where some new information becomes available to quote unquote the public, which makes an MEV opportunity evident. Maybe it's a change in an external price, allowing an arbitrage. Maybe it's a change in an internal price, allowing a back run or some sort of DEX to DEX arbitrage. Maybe it's some event in the outside world. But in any case, some information becomes available, and this becomes evident. And now the first transaction to exploit it in first come, first served will capture a reward, right? Whoever gets into that internal transaction queue inside the sequencer first, they're going to run first, they'll get the reward. So the result is a race. How do you get an advantage in a race? Well, maybe you get the information about what happened earlier. Maybe you can deliver your transaction to the sequencer faster. Maybe you just get lucky. Right. So there's some simple economics of racing here, which is worth looking at. So the racer's transaction, because it's racing and doesn't know it's going to win, will typically look like this. First, it'll check if the expected opportunity really still does exist. If so, it will exploit it, otherwise revert. Right. And so under what circumstances is this a good idea for the submitter to do? Well, you can say, well, what if the expected opportunity exists with probability P? If If that's the case, we'll get a reward R and we'll pay a cost of C times G, where G is the gas price and C is the cost per, right? And or with probability 1 minus P, we're down here and we pay some other cost, DG, right? And so it's easy to calculate this is worth trying if the probability is at least this threshold amount. Notice that this, and then, you know, sort of the simplest calculation from there is, well, if you have a bunch of equally situated parties, identically situated parties, how many of them need to be racing if they all have equal chance of winning before it's not worth adding one more? And the answer is just this, easily calculated. The number of reverting transactions you expect is exactly this. So notice that if the reward R is large, or the gas price G is low, or D, the cost of reverting is low, you expect to have a lot of reverting transactions. And in fact, what would happen in that case, if let's say R is very large in practice, is you get so many reverting transactions that it would drive up the gas price, and then G is not small anymore. And in fact, what you would see is a flood of reverting transactions until the gas price goes up enough to crowd out more of them. But of course, there's the external effect then of crowding out all kinds of other traffic. So a bunch of takeaways. Racing effects dominate MEV dynamics. MEV opportunities get exploited very quickly because it is a race. The goal is to be first, not top of block. Where you are in block doesn't matter. What matters is all that matters is whether you get into that internal transaction queue faster than the other person. The block time, in fact, here really only has second order effects. It's a really important thing about first come, first served MEV, that it's not about blocks, it's not about block time. It's about getting into that queue. The MEV value is partly captured by the searchers, but it partly goes into a couple other things. It's partly dissipated on the searcher's investment to reduce their latency in order to become fast, or into gas fees for reverting transactions, right? If you try, you might succeed or you might fail. And if you fail, you're spending on a reverted transaction. The good news here is that MEV competition might increase the chain revenue because of these reverting transactions are paying gas to the chain and also maybe driving up the gas price. The bad news is that if that happens, it's due to the gas used by wasteful transactions, and it has external effects on other transactions that are negative.
So what's your co-location fee for your sequencer?
There is no co-location fee, but when we get to time boost, we'll get there. Okay, can we add a revenue capture mechanism to this where the chain directly captures revenue from MEV? A couple advantages to that: it internalizes revenue for the chain. It reduces, ideally, the searcher's spending on latency and reverting transactions, because if you're somehow paying to the chain in order to get a share of the MEV, that leaves less left over for this wasteful competition on these things. The disadvantages here are that all of the known approaches to this increase the lifetime of arbitrages, and that means they increase the loss versus rebalancing, and so more gets extracted from liquidity providers. All right, priority gas auction, next model. Within each block, you order the transactions but in decreasing order of priority fee, breaking ties by arrival time. The implementation of that looks like this, just like before, except this queue is now a priority queue that spits out the highest tip transaction first, breaking ties by arrival time. All right. Economics here, you're replacing the racing with an all-pay auction or something like it. You still get reverting transactions from the auction losers because it is an all-pay auction. Rational searchers will wait and submit only at the block deadline. If you might get more information that helps you make a better bid or decide whether to submit at all, you might as well wait until the end of the block time and submit your transaction at the last minute. So because people wait until the end of the block deadline, it increases the lever because arbitrageurs will wait until the deadline instead of racing to submit immediately. The latency investment, by the way, here, if you invest in decreasing your latency, this allows you to wait a little bit longer. You effectively have a later deadline, and that's an information advantage. And for backrunning type MEV, speculative submission can be rational, meaning that you might, even if you don't know that the MEV opportunity exists, remember that it's worth trying if the probability of success is above some threshold. And so if all you can say is that there's some probability that an MEV opportunity will exist in the future, it might still be worth your while to submit for it in the hopes that it does turn out. And so that speculative submission makes the economics pretty complicated. All right, let me just close out by talking about time boost, which is the other approach that's been proposed for Arbitrum. The idea is you create a sort of express lane. You can think of it as virtual co-location. And your sequencing policy is first come, first served, except that transactions not in the express lane are artificially delayed by some small delta t, maybe a couple hundred milliseconds. You then auction off exclusive control over use of the express lane for a period, like say a minute. And the auction winner can control admission to this express lane. Any transactions that they say should get express lane treatment will do so. So basically what you're doing is you're selling a head start in latency races. And what you're trying to do here is sort of hit a sweet spot where you're selling a head start that's big enough that someone is willing to pay for it, and where everyone else is sort of intimidated out of the latency race, so you don't have so many reverting transactions. But that head start is small enough that that party still has to act pretty quickly. Right, so that's just implemented again, something like what we had before, except we add this delay buffer, which just holds incoming transactions that are not express lane transactions until and releases them into the queue after the short delta t delay. Right. So the economics here, the auction winner can win any race. The auction winner can wait delta t longer than anyone else before submitting for something like an arbitrage. Again, that has an impact on lever. It increases lever, right, because arbitrage opportunities will live for about that much longer. Latency investment by someone, by a searcher still pays off at the margin because it allows you to have effectively a longer delta t. Or if you're not the auction winner, it makes that other auction winner have a smaller delta t. For backrunning type MEV, speculative submission still might be rational even if you are not the auction winner. You just might hope to get lucky and have your transaction show up during the interval in between. Question?
So you auction just precisely one slot, right? So in effect, you make
Yes.
sort of from a lever perspective, you have a block time of delta t. If you auctioned off more than one
Yes.
time boosting, then you get the best of both worlds, right? The lever would still be zero, but at the same time, you wouldn't get the
yeah. If you auction off multiple spots, the tricky thing here is the Sybil problem. If you auction off 2 slots, for example, the rational strategy is to bid twice, buy them both, and then you're back in this situation. So the Sybil issue here makes that strategy more complicated. And
Have to pay more though? If there's someone that's willing to pay $10, you auction.
oh, the reason for this is that if you sell, let's say there are 2 slots, if you sell the 2 slots to different people, then those people have to race. And so there's they have to submit quickly. They can't wait the delta t, right? And the advantage of that is that you don't have this increase in lever. The disadvantage of this is that those 2 parties collectively make less money than if they colluded and agreed to just sort of to just let one of them win, right? And so either you get collusion or else you get a party who just bids twice wearing 2 different hats as Sybils, right? And if I do that, then and I win both, then I have exclusive access, and it's more profitable for me than and I make more than the sum of what 2 competing people would make, and therefore that's why the multiple seat version of this auction is complicated. I'm very low on time. There's a lot of actually interesting variations on time boost. This is one of them that we could talk about, but well, I'm going to have to take those offline. Let me. Good question here.
There's no way in which I can actually ensure a certain bundle in any of these settings, right? Like,
so one thing you can do, and one thing that many of these sequencers do, is they allow you to submit a bundle of transactions where the sequencer guarantees that those will be put into that internal queue consecutively, right? And so you can do bundles independently of this. All right, what's the current state of play? All of these policies are deployed on some major L2s, the exception of time boost, which is proposed for Arbitrum 1. There are many open questions about the equilibrium outcomes, many open questions about the economics of this. I've sketched, and maybe sketch is even a generous term for what I've done here, but tried to give you some idea of what the issues are and how they might play. A lot of interesting research going on here. In the future, I think we'll see for at least some chains a move to committee-based sequencing that affects the design options, but sort of the ideal functionality you want from a committee-based sequencer is something that behaves like an honest centralized sequencer, assuming that the committee is supermajority honest. Another future issue here is enabling MEV recapture by applications, which can be done in either priority gas auction or in time boost, simply by making visible to the application what the sequencing status of the transaction was, how much it bid in priority gas auction, or whether it was in the express lane in a time boost. And what that does is it lets applications price discriminate based on that information, thereby recapturing MEV. And this works especially nicely, actually, for things like applications like AMMs. A lot of interesting research and options there. The best analysis of all this though has to account for the realities of L2 design, including what you need to do to prevent abuse and free riding, and as well as issues of security against malicious sequencers. So I think this is a deep and interesting research area that has kind of exploded recently, and there's going to be more interesting work going on these topics. All right. Thanks, everybody.